Okay, here we are.
Wait, okay. I'm trying to click this. Oh, okay. Okay. Okay, so various things are different today, so we're not sure how this is gonna go. I don't have my tablet working and stuff like that. So I'm trying, yeah, I mean, if I need to show you pictures, I may draw them on pen and paper. We're not sure how this is gonna go. But that's not even the main reason that things are different. So what I'm going to talk about today is a sort of it's a little bit of a change of pace, and I'm going to be talking about Galois theory for beginners. Now, maybe that's not a change of pace, because maybe that's what I'm always talking about, Galois theory for beginners. But maybe, I don't know. This is something that I've actually talked about before. I told you a little bit of it, but I haven't yet told you all of it. I mean, I guess this is sort of like, you can think of this as a story of the quartic formula versus the quintic formula. And I guess the quartic formula wins because it exists. And so I when I think about this, I was wondering, you have this penchant for thinking about exceptional things. So I guess whether you've thought about this from the point of view of, the idea that there's, right, sometimes there are these infinite series of things, but then sometimes there are infinite series that kind of peter out after a while, so they're not really infinite. And do you think of this one that way at all? I mean, there was this historical progress, mathematics from the quadratic, and then all of a sudden it came as possibly as a shock. This is one of those things that I think of as sort of modernistic thing. When people find out that the solution to a problem is that there is no solution.
Yeah.
And I mean, there are examples of that really early in mathematics. This one isn't that early, but it's still notable. So, right. So, I mean, so what are the prerequisites here? I guess I was aiming this talk at people who have people who are familiar with the quadratic formula. Maybe they couldn't rattle it off unless they really tried to think about it or something like that. But and maybe they've heard that there are others, but they don't really know much about what they are. And that you shouldn't know too much more than that. So maybe we both meet those prerequisites. Yeah. So this is supposed to be a kind of story about why is there the quadratic formula, the cubic formula, the quartic formula, and then all of a sudden there's no quintic formula. And this is, arguably the origins of Galois theory. And although you could really argue about that. Although in a way this story goes back, it is kind of important that this goes back before Galois. This whole idea of the unsolvability of the quintic. There's this guy Ruffini apparently who did it, and it could be that the way I'm going to do it is more like Ruffini's way. Then like Galois way, but I'm not really sure because I don't really know the history. As usual, I don't know the actual history, but this is sort of like this is a sort of this is one idea about how to try to explain Galois theory to a beginner. So, so let me tell you what a okay, I'm gonna give you a definition. Okay.
Okay.
So this is what I call a color wheel decoration. And so a color wheel decoration, I guess, yeah, I'm not sure exactly how general to do this, but it's like we're going to have some sort of geometric object, which perhaps has some symmetry, but then we're going to think about decorations, extra decorations that you can add on to this geometric object that may mar the symmetry in some way. So a really important example that for us is going to be like the n-dimensional simplex. So let's think about that. Let's think about the n-dimensional simplex, and we're going to think about decorations that we're going to add to this. So what are decorations going to be? Well, I'm thinking of, like, for example, the 3 simplex. And the 3 simplex, I can hold it in my hand, and I guess it's also called a tetrahedron or something like that. And I could, like, write on it on this tetrahedron. I guess, if I had the right dimensionality of pen, I could write on the interior of the tetrahedron. Do I need that? I don't want to worry about that. It's particularly for the example of the tetrahedron. Let's think in terms of writing on the surface of the tetrahedron. And perhaps with a multicolored pen, so maybe you can paint. And okay, yeah. So this, yeah. So there's going to be a color wheel involved. So by a color wheel, I just mean a finite set of colors, like maybe red, blue, green, or something. That could be the 3 colors. But it's somewhat important what's the number of colors is that you have. Okay, I mean, you get to change your mind about what the number of colors is, but at a particular point, you should know the number of colors in this color wheel, and you just arrange them in a wheel. So there's like a cyclic order on them or something like that. And the decoration is going to be, I don't know. How are we going to formalize this? It's not really very important. Let's make it like, for each of the colors in this color wheel, the color wheels, I guess it's sort of like an easel or something like that. Is that what? No, not an easel. What do you call it? What, palette? Is that what it's called? Huh? Palette. Where did I say easel from? Okay, must be the other piece of equipment that you had. So the sorry, I'm just really confused here. What the hell is an easel? I can't even remember what an easel is.
That's that flat thing that you daub paint on to get yourself some mixed paints to then dip your brush into. So you form.
I'm not even sure I ever knew that, but okay. Okay.
It's there's traditionally sort of vaguely heart shaped. You may have seen cartoons of a painter holding this.
Yeah, I'm visualizing something, but maybe I usually hear people say the word easel, and I never really figured out what part of that equipment for the easel. But yeah, right, and it's not like we don't need it, because we're not really going to mix colors. So we're going to have, like, each color is going to give us like a disjoint subset of the surface of this tetrahedron. Okay, that's what this decoration consists of. We're gonna have, like, let's say we have 2 colors, black and white. So we're gonna have like I mean, maybe we just have a map from the surface of the tetrahedron to the two colors.
Okay. So it's completely painted.
Yeah. All right. I mean, that, that might be giving us too much liberty because you can, have all sorts of fractal things or something like that. But let's think of that. Let's think that this decoration is a map from the surface that we're decorating to this finite set of colors. Now, black and white, that's a two-element set of colors, but they're not very colorful, but that's okay. Okay, so let me tell you what so that's what a decoration is. But now I mean that's not what we haven't finished the definition of a color wheel decoration. So it's supposed to have a certain, I don't know, symmetry property or something like that. So the three simplex that we started out with has just some geometric symmetry. I guess at this point, let's think of it as rotational symmetry. Let's ignore the reflection symmetry. Let's just think of the rotation symmetry. So I guess it's important for me to say that this is supposed to be different from usual. And one of the ways it's different from usual is that usually I'm talking way beyond my own level of understanding. And that's my general all-purpose excuse why things are hard to understand, because I'm talking about things that are way beyond my usual level of understanding. But that's not what I like to do. What I like to do is talk about things that I do understand. And theoretically, that's what I'm supposed to be doing today, talking about things that I do understand. And so that might make you think that, okay, that you should be able to understand what I'm talking about today. But I just have so many alternative excuses that you have to, you have to allow, you have to make allowances. So like one is that I don't have, that there's all these pictures that I want to show you, but the tablet isn't working. And even if my tablet was working, some of the pictures that I want to show you are like really elaborate animations and things. And I can't do that. So I'm going to have to, some of the pictures that I want you to see, you're going to have to see them in your mind. I'm going to describe these elaborate pictures or elaborate animations, and you'll have to try to see them in your mind. So, yeah, so I have all sorts of excuses here. So, you have to imagine this color wheel, this little palette, this circular palette of colors. Is that reasonable pronunciation of the word palette?
I just say palette, but I'm confused. Now you're making.
I have no idea.
Yeah.
So it sort of has, this rotational symmetry to it. And so there's a really strong constraint here that I'm trying to describe now about what you need, what the decoration needs in order to qualify as a color wheel decoration. So the rule goes like this, that and it's supposed to be a definition. It's supposed to apply to more generally than just this tetrahedron, but I'm really describing it just in the case of the tetrahedron right now. Okay. So the tetrahedron has these. Okay, I have to think how many rotations does it have. So it has 12. Is that right? 12 rotations, because it's got 24 permutations of vertexes, but half of those are odds. Is that what they're called? Permutations, and it's only the 12 even permutations that give us the rotations. And So imagine that you've got, well, so let's say you rotate the palette by 1 notch. Okay, then the decoration is supposed to have the property that if you apply that rotation of the colors to the decoration, then it will appear to the viewer looking at the tetrahedron as though the tetrahedron has undergone some rotation.
Okay.
And so, I mean, what am I trying to say? I mean, this reminds me of certain things that I'm not sure how early these things go back to. I'm not sure they go quite back to the time of Ruffini and Galois or something. I guess Galois is around early 1800s. Ruffini maybe also, or a little before that. I'm not quite sure. But there's this thing called chasing lights. You know what chasing lights are?
Nope.
It's this thing you see on a theater marquee.
I don't know.
I mean, it's got
Lights going by.
what?
I don't know. I can imagine things.
I mean, you've got lights on in a somewhat circular pattern around a. I mean, it could be rectangular, but it's in a somewhat circular pattern going around a. I mean, what happens is what happens is this. It's a kind of electrical decoration on lights on a theater marquee that gives the illusion of motion. But really, all that's happening is that the lights are changing colors.
Yep. Yeah.
So make it look like it's rotating or something like that, when really it's just. You can make it look like a geometric rotation when really it's just a rotation in abstract color space. And if you take this principle very generally, then you can make all sorts of motions appear. But the definition of a color wheel decoration is this idea that just as you perform one of these abstract rotations in the color space, it appears to the person watching the tetrahedron as though it has undergone a spatial rotation. So let me give you an example, okay? Let's do a color wheel decoration with 2 colors, black and white, okay?
Okay.
But I think I'm going to do, instead of the example of a tetrahedron here, I'm going to do a cube, okay?
Okay.
So can you come up with an example of that?
I could do a tetrahedron.
Well, I don't want you to do a tetrahedron. I want you to do a cube.
Oh.
Do it to a cube.
Since when did we do a cube? Okay. Okay.
Well, I just suddenly realized I was going to. I'm doing this very disorganized way. I suddenly realized that I described it for a tetrahedron, but it still makes sense for a cube. So we're going to have a color wheel decoration of a cube. So a cube has how many rotations? 24 rotations.
24. Yeah.
Okay. And but can you come up with some decoration of the cube with 2 colors, black and white? So every point of the boundary of the surface of the cube is painted one of these 2 colors, black or white. And what is and can you make a color wheel decoration from this with the 2 colors, black and white? And how are you going to do this?
So let's see. So
it has to look like the cube is rotating every time the color is rotating.
Yeah. Some reason.
Yeah.
So I can't just color each face with one color, black or white, I think, because then two faces have to be one color at around a corner and the other one has to be the other color. And so now that's not going to work.
You're saying it won't work if you just color each face a solid color, a solid black or solid white?
Yeah, not unless I color them all black and do some stupid degenerate thing. But if I color them, well, it doesn't seem like it's, well, maybe, oh, I don't know. No. So if you'd given me 3 colors to work with, I would find it easy.
Maybe I should give the example for the cube, and then you'll try to find the one for the tetrahedron.
Well, what I was going to say is that I think I need to chop the squares faces in half.
Well, remember, you know, it's not like you don't have to make each face solid color, or you don't just get to color the vertexes. You get to color any part of the surface you want at all.
Leave a bunch, so you can, but you can't leave a bunch uncolored.
Right.
Okay. Okay.
I'm still trying to figure out if you're right about the faces solid colors. Could you explain to me an argument for why that wouldn't give you a color wheel decoration? I didn't quite follow your.
I mean, if the faces aren't all the same color, so there actually is a white face and a black face.
Yeah.
And there's got to be I don't know, but there has to be a corner where there are either 2 white faces. I'm coloring faces here. So there has to be a corner, there are either 2 white faces and 1 black, or 2 black and 1 white.
Yeah.
And so we can't have a rotation around that fixes that corner, because that would not get mapped.
Yeah.
So let's see. So okay. So then
I mean, maybe you're right. Maybe you're right.
I haven't killed it completely.
All right. But okay. But I'm willing to not worry about this at the moment. But I want to think of, can you come up with, using some other kind of coloring of the surface of the cube with 2 colors?
Yeah.
Can you make it into a color wheel decoration?
Yeah. So then I think if I hold the cube by its 2 opposite corners, I hold the cube by 2 opposite corners.
Yeah.
And my goal, this isn't going to work. Okay. My goal is to make it's still not working well. My goal is to rotate while fixing those 2 corners. And I still don't like that. No, that's not good. Because that's a rotation of order 3. And so I need to do a rotation of order 2. Okay. So the switch white and black. Okay, so what I'll do is I'll hold an edge and the opposite furthest away edge.
Yeah.
And I will, the rotation I want to implement is the one that maps each of those edges to itself, but rotates it 180 degrees. So I'm grabbing the cube by the 2 opposite edges.
2 opposite edges, yeah.
And I'm going to flip those edges over.
Yeah.
I want to make sure that switches white and black.
Yeah.
And I think there's going to be a way to do it. So like, there'll be 2 squares that are special with respect to those 2 edges. like if my two edges are oriented vertically, then there's the face on top and the face on the bottom. So one of them is going to be white, and the other is going to be black. Right? And then if I flip the cube over along those two edges,
Yeah.
the white and the black will interchange. And then I have these four other faces.
Yeah.
So if you look at me, there'll be like two faces. These are those two edges.
Yeah. Yeah.
There'll be like two faces facing me and two faces facing you.
Yeah.
And so two of those, the ones facing you are white, and the ones facing me are black.
Yeah.
Then I think everything works. That switching white and black is the same as rotating that cube 180 degrees.
All right. First of all, let me ask something. Supposing, okay, I'm changing the rules here as I'm going on. Supposing I do allow an extra color invisible here.
Okay.
Does that make it any easier or easier to describe the picture? So, I mean, you could make everything invisible except for just the vertexes, or everything invisible except, everything, yeah. Invisible means colorless, I guess.
Yeah, that's what I was asking you earlier. Yeah.
I didn't think I would need one, but now it seems like it helps.
Well, I thought I did it without that extra trick, but you didn't. But anyway, it doesn't change anything that much. But I could.
Yeah.
Same story. Now I just need to color the top face white and the bottom face black, and everything else colorless. And then turning the cube upside down is switching those two.
Okay. Sorry. Maybe I haven't said things right yet. Then let's see. So okay. So what do
you don't want to allow that?
No, maybe I just didn't say. Maybe I just didn't. Well, maybe I didn't say the definition correctly. So okay. Yeah. Okay. I guess I said it completely wrong. Let me try to describe it what it's the right way. So yes, if you just rotate the colors, then it should look like if you rotate the colors, then it should look like the geometric object has rotated. But I want it the other way around too. If you actually rotate the geometric object, then it should look like the colors have rotated.
Any rotational symmetry of the cube then?
Yes. Yeah. So I probably totally screwed that up by not saying that.
That certainly wasn't true. Okay.
So yeah, right. We will allow, not every point of the canvas needs to be painted, but the ones that are painted have two choices. Let's say them, I don't know, black and white or whatever your two choices are. But there's, this third unpainted color. And yeah, it has to work both ways. That when you rotate the color spectrum, it looks like the geometric object is rotating, but also vice versa. When you rotate the geometric object, it should look like the color wheel is rotating.
Just seems like it'd be easier to do all these if I got three colors. Then I would color the three diametric opposite pairs of faces, the three different colors. Is that legit?
Can I think about that?
Uh-huh.
You're totally screwing me up here because you're making the hard questions easy and you're making the easy questions hard.
Well, you should probably tell me what answer you wish that I'd said.
Well, let me think. Right. I should. Okay, so let me tell you what I would have done for the. This is what I should have done. Right, I'm totally screwing up here. But for the two colors for the cube, I simply would have alternately colored the vertexes.
Okay.
So that's really simple.
Yep, that's fine.
But
That's
given that as an example.
uh-huh.
Now, are you see? So did you yeah, okay. Well, let me ask you this for the tetrahedron. Let's think about the tetrahedron now. Let's think about the tetrahedron. Can you find a color wheel decoration for the tetrahedron?
The two colors.
Any number of colors, 17, 5, 3, 4, 2, just not one. You know, one doesn't really count as a color wheel decoration.
Well, so the rotational symmetry group of the tetrahedron is famously A4, the alternating group on 4 things. And you can think of those, well, okay. Think of those 4 things as the vertices. And
yeah,
well, let's see, but that's not good. No, but that's not good. So okay, so if I color the vertices with 4 colors, I can get even permutations of those colors, but you want cyclic permutations only. So that's no good.
Are you telling me cyclic permutations? Wait, cyclic permutations? Oh, cyclic permutations.
Cyclic permutations of 4 things that in the sense of cycling around some cyclic 4-element group.
Yes.
Well,
But
anyway, so maybe 4 was a bad choice there. Anyway.
Sorry, what does cyclic mean? Cyclic in what sense?
In a cyclic group.
A
single cycle.
Oh, a single cycle. Okay. So what's the those are what parity in the on a 4-element?
They are both. The generator is odd.
The generator is odd. Okay.
So that's bad. Well, I don't know. That's
okay.
Okay. So
you don't have to use 2 colors if you want. You can use 7.
Right. I was using 4. Foolishly, use 4 colors. Okay.
Oh, 4 colors. Oh, I said you don't have to use 2, right? And you weren't using 2. You were using 4. Okay. Yeah. Go ahead. Yeah.
I should say that I haven't had nearly enough sleep last night.
That's okay.
My excuse. You've got your own excuse. So
right. I have plenty of excuses.
Okay.
No, this is actually one more excuse for me. Okay, go ahead.
Okay. So, how many colors do you want me to use?
That's part of the puzzle, is to try to figure out.
That's too makes it too hard. Constrain it in a way that's.
Well, see, I'm a little bit worried that you already gave away the answer with your cube thing. That like your cube answer. Does your cube thing really work? So what am I trying to say? So you're telling me that with your cube thing, you're telling me that any, right? You have to give just rotations of the color spectrum, not transpositions. Mm-hmm. And so yeah, so right. So you described the 3 opposite faces of the tetrahedron, of the cube, 3 opposite faces of the cube. 3 pairs of opposite, each pair of opposite faces gets its own color. So that gives us 3 colors.
Yeah.
And is it true that those always cycle every time you rotate the, as opposed to just switch? Yeah, I guess, let's see, is that true? There's never a fixed color, is that right? Or is there a fixed color?
from some rotation of the cube.
Yeah,
Any rotation.
I guess there is. Yeah, is that right? Yeah,
Hmm?
so that doesn't work. That doesn't seem to work for the cube.
Uh-huh.
Is that right? I mean, don't you know?
Yeah, if I hold the top
My
and bottom
mistake.
cube,
Yeah.
top and bottom face fixed and rotate 180 degrees while keeping them fixed, then all the colors are mapped to themselves. So you want to get a non-trivial, I don't think you ever said you have to get a non-trivial rotation out of any way of.
No. I'm distinguishing between a rotation of the colors and a reflection of the colors.
Oh, well.
Um,
Yeah, you're right, but you're getting it. Right, we're getting an odd permutation of the colors. Well,
yeah.
yeah.
See, now you really got we worry about whether it's possible for the tetrahedron, but maybe there is some difference between the tetrahedron and the cube, which is going to make it possible for the tetrahedron. Let's see. So what do the tetrahedron got?
So, okay, so I mean, somehow it's, even though you're supposed to be trying to pitch this at a level where someone's not supposed to be using group theory.
Right. It's much better if you don't, but go ahead. Yeah, you're going to.
Yeah, well, it seems too hard to solve if I don't know group theory. If I don't use group theory.
I mean, what you have to do is you have to actually, take a tetrahedron and go a little on. Yeah, go ahead.
Yeah. No, I mean, I eventually would figure it out, especially if I had a tetrahedron.
Right.
But anyway, so you must be secretly saying there's like a homomorphism from the symmetry group of the tetrahedron to something like S3.
I have to admit that's what I'm saying. Yeah, go ahead.
Yeah, to S3 or just to S2. Well, the S2 is there's the
Depends
sign.
on
No, never mind. That doesn't make sense. So from A4 to S3. Sorry, not from A4 to S3, from A4 to C3, the cyclic group on.
I think that's right.
Okay, so what are those three things in the tetrahedron that are getting cyclically?
I mean, is that right? Let's see. So
I think of it like the opposite edge pairs of opposite edges.
That's what I think they are. Yes.
Okay.
But how can this be working? How can this work if the cube thing doesn't work?
Well, the cube has a bigger symmetry group than the tetrahedron.
Oh, so you think that bad one with the cube isn't a symmetry? It doesn't come from a symmetry of the tetrahedron?
Yeah, there are two tetrahedra that you can inscribe in a cube.
And that is switching them?
Yes, that is switching them, I think. Is that true?
All right, that may rescue us. But so, yeah, okay. But so am I getting this right? So it's there's so many ways. It's so easy for me to get things backwards. I mean, you're saying that there's this homomorphism, and the image of the homomorphism is this cyclic group. I'm just worried I'm getting it backwards, and it's really supposed to be the kernel is cyclic or something like that. But maybe it is the image that is cyclic or something like that.
I think that's the great thing about A4 is that it has some interesting quotients, more interesting than your average alternating group. More interesting non-trivial homomorphism.
I guess this is right. Yeah, because right. How do we get to it? Right. Well, okay. So Right. So we're totally screwing this up. But the way this is supposed to work is that, you give the students a chance to try to discover this decoration by themselves. And the decoration is, again, let's say it out loud. You've got this regular tetrahedron, and the color wheel decoration on it is you need 3 colors. Let's call them red, blue, and green. So you take one opposite pair. So you can talk about opposite edges of the tetrahedron. That's why I'm trying to hold my fingers in a funny way or something like that. And I mean, I guess I was thinking of just putting one dot of color right in the middle of each edge, but you could make it, I guess, the whole edge. So each edge, each opposite pair of edges gets its own color. So that's 3 colors right there. Red, blue, and green. And if we didn't screw up, then that actually does meet the definition of a color wheel decoration. That as you rotate the colors, it looks to the naive observer as though the tetrahedron has rotated, and vice versa. That as you rotate the tetrahedron, it looks like the color wheel has rotated. And so that's the way the demonstration is supposed to go. You're supposed to give the students the chance to discover this color wheel decoration for themselves. And then you explain to them, then you tell them what they have actually discovered, what they've actually invented. And what they've actually invented is the quartic formula. So that is the quartic formula, in a sense.
Well, you explain that part.
Say it again. You do want me to explain that part?
Yeah, I want you to explain that part. I mean, I know
Right,
that
that's the whole point,
the
right?
quartic formula, but seems like
Right, and in a way, you already know this, but you're an inferior substitute for an ignorant student.
I mean, at least pretend I'm going to demand my explanation the way the student would. I'm going to milk it for all the word.
Right. So how does this work? Well, so what is the quartic formula? So it is a solution by radicals of the general quartic polynomial. And you have to understand what that means. Right, let's think a little bit about trying to say what it means. So I guess the big thing about these polynomials is that there are 2 things that a polynomial has that are very important here. And one of them is coefficients, and the other one is roots.
Yep.
And it's kind of like the coefficients are sort of like, I'm going to say the coefficients are sort of like the inputs and the roots are the outputs. Maybe that's not the way you usually view it. You just think the unknown is like the input or something like that. But we can think of it this way, right? That
put in an ordered list of coefficients and you get an unordered list of roots.
Right, I guess, right. Well, I guess, right.
I'm a set of roots, multi-set.
I mean, I was distinguishing between the roots and the unknowns, but the roots are something like the unknowns or something like that. I mean, it's just funny that there's more than one solution or something. There's more than one root. So what am I trying to say? That there's a completely straightforward way to get the coefficients of a polynomial if you know the roots. And that's just because you for each root gives you a linear factor, and you just multiply those linear factors together. And but the whole point of the solution by radicals is that we're trying to go the other way. We're trying to know the coefficients and get the roots. And we want a formula to do that. And the formula is right. And there's sort of restriction here according to the traditional rules, which is that this formula should involve radicals, or shouldn't involve anything else but radicals. So radicals are, nth roots.
Mhm.
And one of the things that makes it tricky, right, is that we said that it's completely straightforward to get the coefficients from the roots, because you just have these linear factors and you just multiply them together. Multiplying, it's just a completely deterministic operation. It's a function. Function means deterministic operation, roughly speaking. But inverting it is not the inverse is not a function. There is no inverse. So in other words, there's an ambiguity. It's like a so-called multi-valued function. If you try to do it in backwards, it's not a function. It's not a deterministic process. You don't get a unique solution. So there's an ambiguity here that, again, I'm saying this in a sloppy way, but it does make sense. That if I mean, I guess right. Maybe what I should be saying is that you with the coefficients, you clearly have them arranged in order. There's the constant coefficient, the linear coefficient, the quadratic coefficient, et cetera, et cetera, et cetera.
Mhm.
But the roots, this is the same number of roots as coefficients, if you think about it. Well, to get that to work, maybe we should make it like a monic polynomial or something like that. Is that right? So monic polynomials will give us the same number of roots as coefficients. But there's no obvious favorite order on the roots.
Mm-hmm.
And that's this ambiguity in figuring out the roots. Whereas, right. So getting the coefficients from the roots gives you the same result, even if you permute the roots, which sounds like a good thing, but it's a bad thing when you're trying to go the other way. Because when you're trying to go the other way, if you're going to get multiple possible, or you're going to get a multi-valued function, multiple possible orders as a function of the coefficients, and that ambiguity, that's where Galois came in and said he was going to invent this thing that he called the theory of ambiguity, I think, but people called it group theory by some misunderstanding, but it's really the theory of ambiguity. It's the theory of multivaluedness of functions. It's the theory of the ambiguity of the output of a function, of the value of a function. Functions are supposed to be deterministic. There's supposed to be, in some sense, just one answer, one output, one value. But in situations like this, where you have a multi-valued function, the answer is ambiguous. And that means that the theory of substitutions, group theory, or the theory of symmetry, theory of invariance, is a useful tool in analyzing what's going on, in understanding the multivaluedness of these functions, the multivaluedness in particular of the function that gives the roots from the coefficients. So yeah, I'm just trying to beat it into my own head here, that getting the coefficients from the roots is many to one, because of the many is the many different orders, many different permutations of the roots. But that means that going the other way around, getting the roots from the coefficients is one to many. It's ambiguous, multivariate. And that's where Gauss's theory of ambiguity comes in. So, So I'm trying to justify the claim here that this student who has solved this problem has reinvented the quartic formula, which is a solution by radicals of the general quartic. And the basic way it works is, I don't know, you don't want to try and guess. The basic way it works is that, let me see if I can say this right. The radicals are the colors in the color wheel. So, right, I mean, taking radicals, right. So, what we're sort of trying to say, a solution of the general quartic by radicals is a way of simulating the ambiguity of the roots of the general quartic by some combination of the ambiguity of ordinary root taking. So the ambiguity of ordinary root taking is this wheel cyclical thing. And the job of the quartic formula is to simulate the total four-bang symmetry, the four-bang ambiguity of getting the roots of the general quartic, simulated that by some combination of the cyclical ambiguities of the radicals. So what happens is that the right. So in general, when you give a solution by radicals, you're going to perform a series of these cyclical symmetry breakings. Each cyclical symmetry breaking is where you're taking a root. And your job is to start out with the symmetry of the object that you have, which will actually be a full four-bang for the general quartic. And your job is, by a sequence of cyclical symmetry breakings, your job is to completely break down the symmetry until it gets down to nothing. And in the case of the quartic, let's see how that goes. Let's see how that sequence of cyclical symmetry breakings works. Okay. So what have we got? We've got 24. The permutations of the four roots. And then the first one, the very first thing that you do is this discriminant thing. I mean, this is where you actually break it down from rotations and reflections to just the reflections. Just the rotations. Just the rotations. So how does that work, right? That should just be, let's think about that, right? And the rules are a little bit different here because we're not trying to get the color wheel to correspond to rotations of the tetrahedron. We're trying to get the color wheel rotations to correspond to the arbitrary permutations of the vertexes of the tetrahedron. So we're including reflections as well. But right, there should be some way to do this, right? It should be just two colors. Am I missing something here? What is the obvious thing here?
So two colors that get interchanged when you reflect.
Yes. Okay. I just figured out how to do it. It's amazing how I can forget these things, but I just finally remembered how to do it. So can you think of that? Can you think of the color wheel, two colors, just a two-color color wheel decoration for this tetrahedron that will, get us down from the symmetries that we're starting with, which is both rotations and reflections, to get it down to just the rotations. Am I thinking it right?
I don't know. I'll guess something. So is there like a way to like draw a little letter R on two faces in black and a little backwards letter R on two other faces in white?
Something like that should work.
And so the only way we can map those white R's to those
Russian, what?
reflection. A suitably chosen reflection.
Well, let me tell you what I'm thinking of, and then you can tell me what you're thinking of is the same thing.
Okay.
So I'm thinking just barycentrically subdivide each face of the tetrahedron. And then just alternate colors everywhere. Right? Once we barycentrically subdivide each face, we've now, really we're barycentrically subdividing the whole tetrahedron, I guess. So now we've got at least 24 little things there.
Okay.
And if we just, so it's like the odd ones are being colored black and the even ones are being colored white, and that'll do it.
Yeah.
So yeah. So that's the first step. That's going to get us down to where we just have to do it the rotations. And then comes the tricky thing, the thing that's supposed to be the thing that the student invents for themselves, which is the three opposite pairs of edges of the tetrahedron. Each of those gets its own color. And that gets us down from what? That gets us down from the 12 rotations to just 4 things. Is there some way we can geometrically describe what those 4 things are that's left? Those are special 4 rotations.
Those are like these. Those are like this. Sorry, I'm trying to get the Klein 4 group coming in, and so it's something
that is the Klein 4 group. Yeah, that's the Klein 4 group. What we've broken it down to.
Right.
And once you get down to the Klein 4 group, then breaking that down by cyclic symmetry breakings is going to be pretty easy. So right, there was that one step at the beginning where we did the barycentric subdivision and the black and white coloring of the odd versus even, and that's something you do for any simplex, even 17 simplex or something like that. So that's completely, what's the word I'm looking for? That's completely unexceptional. But then for the 3 simplex, for the tetrahedron, there's this very exceptional thing where you can have a 3 color wheel decoration that'll get you down to the Klein 4 group. And that was the one that was supposed to be the fun one to reinvent for yourself. And then at that point, you're down to this Klein 4 group, and then it's really easy to do the rest. So you've got, you can break the symmetry of the tetrahedron down by this sequence of cyclic symmetry breakings. And that is essentially the quartic formula. We can almost literally just turn this into the quartic formula if we think about it. But let's think more about this sequence of cyclic symmetry breakings. So it's like it's this parity coloring in the beginning. And then it's the tricky 3 coloring one. And then it's the 2 boring 2 color ones or something like that. So each time you do one of these 2 color ones, it should just be taking the square root. And each time you do, well, there's only one time when you do something that's not a 2 color one, and that's the 3 color one. And that is, that's corresponding to taking a cube root. So it's like we're sort of predicting that if you look in a textbook and look at the quartic formula, then in some sense what you should find, I always get confused about this, is which order does it happen in?
Right,
What?
yeah, right, yeah. I was just going to ask you, yeah.
Yeah, so it should be something like, I want to say something like, first you take a square root, then you take a cube root, then you take another square root, and then you take another square root. But translating that into what you actually see in the formulas is a little bit tricky, partially because, there are different kinds of chronological order you could use.
Right.
And in fact, it's going to get a little bit. We'll have to see how that goes. But nevertheless, already, even if we were to see at this point and look up the quartic formula, we would already see that it's already reflecting a little bit like what we're saying. You'll see that there's a stage there. We take a cube root, and then there's some other things which mostly involves square roots. And if you think about the amount of ambiguity in it, it should work out to being exactly a 24-fold ambiguity, because that's what it needs to be. We're trying to simulate the 24-fold ambiguity of the general quartic solution by these various cyclic symmetries of ordinary root taking. So, so each time you take an ordinary radical, that's like a symmetry breaking. So it's like going against the grain, right? I mean, like when you respect symmetry, it's just like falling off a log. But when you break symmetry, it's like jumping back up onto the log. Or the way I like to think of it, sometimes I think of it as a salmon jump, right? Salmons love to jump upstream. It's part of their. So that's the way I picture the quartic formula. It's like this sequence of salmon jumps. So I guess there's 4 salmon jumps in this sequence. So, and I'm trying to get the story to make sense. So, like, we have the chronological order of the salmon jumps and everything. So, how does the salmon face their job? So, right, we've got a goal that we want to reach, which is breaking the symmetry down completely. So, I guess, right, it's funny because this is sounding like the contravariance of Galois theory, but I'm not sure if it really is. Maybe it's just some coincidence or something like that. But I've got the smallest subgroup at top. And that's where the salmon is trying to jump up to. And the biggest subgroup, the total group, the 24 element subgroup, is at bottom. And the salmon is trying to plan out this strategy to jump up. And and it turns out this is the last time it can do it, I guess, before the salmon dies or something like that. So, right, it's going against the grain. It's, going against the current. That's why I like to think of it as a salmon making these jumps. But so part of our job here, another important part of our job here is to figure out how does the salmon actually implement one of its steps. And And it's only after we think about that that we'll really be able to put the story together and see how to really reinvent, for example, the quartic formula in your own spare time. And then also equivalently, not equivalently, but also, right, the other part of the story is the, the sort of modernistic part of the story, where we convince ourselves that there is no quintic formula because you can't do this. You discover that, the salmon is dead right from the start. If there's if there's 5 roots, if it's the group 5 bang, 120 elements. Maybe I was being a little bit too critical when I said that the salmon is dead right from the start, because that's not quite true. Because there is, right, you can always just make that first little salmon jump where it gets down from 120 to 60. And then at that point, the salmon is dead.
Now you're giving away the order. Or, well, maybe you're not, I don't know. Well, you made it sound like that's what you do first. But anyway, I guess you're not giving away the order because we don't know what first means exactly.
Well, I mean, but I mean, in the case of in the case of 5 bang, I mean, I don't think I'm giving away too much. I mean, I'm getting right. I'm sort of cheating and saying that we all know that, you can't do it with the 5 bang. But I mean, the only thing that you can do with the 5 bang is you can cut it down from 120 to 60. And at that point, there's nothing else that you can do, basically. There's no cyclic symmetry breakings that you can, there's no color wheel. There's no color wheel decorations of the 4 simplex. There's no color wheel decorations of the 4 simplex. I mean, there is the thing that gets you down from reflections to rotations. But if we're talking about, the rotations of the 4 simplex, there's no color wheel decoration for that. And that, I think, if you go back historically and see what Ruffini did, I think that's basically what Ruffini did. I mean, we'd have to actually check to see if that's what he did. But I think that's basically what he did. He did this exhaustive combinatorial analysis. And it wasn't even that exhaustive. It was fairly straightforward. But I think he basically showed that there is no, because that's what you have to do to show that the quintic is unsolvable, basically. You have to show that there's no color wheel decoration of the 4 simplex. But to me, perhaps more interesting is, rather than the nihilistic thing of showing that there's no solution for the quintic, I'm more interested in showing in seeing how you show that there is a solution from the quartic just by having this scheme for resolving the ambiguity. Mm-hmm. So we already know this series of salmon jumps for 4 bang, but we just need to turn each individual jump into an actual radical that we want to take. So we have to figure out how to do that. So I'm just trying to plot out my time here. So all right, so I'm going to give you another puzzle here. And this puzzle has to do with sort of, the first puzzle sort of had to do with, I don't know, sort of the global strategy for the symmetry breaking. I mean, we only really focused on one step in that symmetry breaking, but still, we had to figure out how to do the symmetry breaking. But now this next puzzle has to do with how to proceed when you already know what the symmetry breaking is, and how to get the formula to work. So let me give you the puzzle here, and then we will try to figure out once again how the puzzle relates to the Galois theory. Mm-hmm. So here is the puzzle. So, right, and I'll try to do this one the way I probably should have done the other one, which is I'll probably try to give you an easy example, and then I'll ask you to try to do a harder example. And the easy example will come with a sort of solution, and you see how it works, and then you try to do the perhaps harder example. So how does this work? I guess this does come with a little bit of hint about how Galois theory works. But what am I trying to say here? So suppose you've got a let me think about how this works. Yes. Okay. So how do I say this? So, let's think about polynomials of two variables, x and y. Okay. I mean, later on we'll have like 3 variables or 4 variables or whatever, but I can illustrate the principle with just polynomials with 2 variables. So supposing let's consider 2 examples of polynomials in x and y, and the first example will be x, and the second example will be x squared. Okay.
Okay.
And they may not look like those are polynomials in x and y, but you don't have to use all the variables, right. So you're allowed to leave some of them out. And the question is, can you express x squared in terms of x and any other polynomials, any other 2 polynomials that you want to use, which are symmetric in x and y? So you start with x, and you try to get x squared, and you're allowed to. Am I saying this right? So let's see. Is there more way? I mean, well, I'll demonstrate this example, and then you have to try to do the hard example. So the thing is, if you look at the symmetry properties of the polynomial x and the polynomial x squared, they are equisymmetric with respect to this one permutation, this transposition of x and y, switching the variables x and y. Because neither of them is symmetric at all. X changes to y, which is a completely different polynomial. X squared changes to y squared, which is a completely different polynomial. But they're both bad, but they're equally bad. So they are equisymmetric. And the basic idea of Galois theory is that equisymmetric things can be defined in terms of each other. Or in order to construct something, all you need is to already have things that are at least as asymmetric as it. And then you will be able to build it from the things that are as asymmetric as this. So an example is you can build x squared from x, because x squared is just as asymmetric. No, did I say that backwards? Because x is at least as asymmetric as x squared is, you can build x squared from x. All you need to build x squared is you just need x. And the way to do it is you just take x and you square it, and you get x squared. But am I saying it right that I want to say that you're allowed to use any symmetric things as well as auxiliary devices. You're allowed to use symmetric things. Maybe what I should say is that what am I looking for? Maybe I'm looking for I guess I said polynomials. Maybe I should really talk about rational functions here. Okay, so let's talk about rational functions. So if you've got Well, okay, so let's say you're trying to define a polynomial G in terms of f. Sorry, did I say polynomial? I guess I mean a rational function here, okay? Define a rational function G in terms of f. And so what I mean by that is, I mean, in general, you could mean, you give a really elaborate theory of how logic involves defining things in terms of each other. But for now, I just want to take what it means is that we have a rational function h, and it has one more variable than the other functions have. And h, am I saying this right? That h should be symmetric in the original variables, but it's not symmetric in this extra variable. Okay. And then for the extra variable, you plug in f, and the result should be G. I hope I'm saying that correct. So, I mean, this is supposed to be a way of formalizing what the intuitive process I was saying. I mean, like, I guess it's a little bit hard to see because it's so ridiculously easy how to get x squared from x, right? You just take, but supposing you have to do it the other way around. So the point is, the other way around seems a bit trickier at first, but see if you can do it. See if you can figure out how to build x from x squared just by, by knowing, so somehow the fact that fact that x squared is as asymmetric as x is supposed to give us the confidence to build x from x squared. And I'm trying to describe what the rules are for building x.
So I get to use x squared, and I get to use x plus y quantity squared.
Yes.
And we get to use x times y.
Yes.
Sorry, I'm really feeling slow-witted, but it seems like that should be like what I need to use. So like, and I'm trying to get x. Okay, that's weird.
Yes. Right, and it's supposed to feel a little bit impossible at first, because it's like, it feels like you're trying to take a square root, and that's not a rational function.
Right.
Am I allowed to give you one clue?
Sure.
All right, so the one clue that I'm going to give you is that you sounded amazingly on the right track already. To an annoying extent. Like I was afraid you're going to rattle off the answer like right away or something like that.
Well, I feel like I almost had it, and then I'm like.
I mean, right. Maybe we should, for illustrative effect, we should try various things out loud, so we can see that they don't work. And
yeah, I can tell you lots of things that don't work, if that's what makes
you feel things that don't work. How you try to
feel better.
X squared.
Yeah, it sounds like that's what you want here.
Right.
So
Again, it seems like you make the easy ones, no, the hard ones look easy, but then I'm wondering if you do it the other way around too. But go ahead, yeah?
So like I can, so you're handing me x squared,
Yes.
and then I've got x plus y quantity squared.
X plus y quantity squared, yeah.
And I sort of like that a little bit because it has, if you multiply that out, it has an x squared in it.
Yeah, I see. This is where it would be good if we had something we could show on the screen here. So,
I mean,
what
oh,
you want to show it on the screen?
I could do this.
Yeah, go ahead. This would be good.
I need to run off and get my tablet. For some reason, I wasn't expecting.
Okay, we can pause this and
Okay, let me just do that.
okay.
Okay, here goes. So the way I'm thinking about it is like, you give me x squared,
Yeah.
and then I can use any symmetrical thing in x and y that I want.
Yes, but
So
maybe I should also say that you're allowed to add and subtract and
Yeah.
divide and multiply.
Yeah, I sort of knew that.
And yes, and then also use any symmetric stuff. That's
Yeah.
right.
Right. So like, here's some symmetric stuff that I get to use. And well, I get to use x plus y for just plain old x plus y, for example, if I wanted to. And so I'm feeling really stupid because I feel like I should be able to like write a formula like x is equal to something built up out of these.
Well,
things.
can I say something about feeling stupid though? Can I say something about that? So the first time I worked on this puzzle was, I was sort of trying to teach somebody Galois theory. And I claimed to them that this should work. I said, oh, by the principles of Galois theory, we should straightforwardly be able to just automatically define x in terms of x squared because, x squared is sufficiently asymmetric that by the principles of Galois theory, we should be able to get x from it.
Right.
And after telling them that, I tried this particular puzzle. And you were lamenting how you were tired and not feeling smart right now. But I was feeling smart at the time. And I thought about it for, I don't remember how many hours, but I worked on this for hours and hours. And I began to doubt that Galois theory was correct because I just could not figure out how to do this. So,
I can see why you felt that way, because right now it's looking,
yes.
It's looking annoying because
Yes.
I mean, just to say some obvious, just to make you feel better. I mean, so
Sure.
So like the obvious things to do, one obvious thing to do is you say like, okay, I'm going to use this cool thing. And then I can use the fact that I've got x squared at my disposal. So I'll subtract off x squared.
Yes.
Sitting right there.
Yes.
So I get 2xy plus y squared. And then you can say, oh, look, but I've also got x. This is not going to help much. I got x times y. So I can like subtract off twice of that. Yeah. This is just going to give me y squared.
Yeah, this is giving me, lump in the carpet feelings. Like, I'm trying to get rid of this lump in the carpet.
Right. So woohoo, well, I got y
somewhere
squared.
Else every time I try to get rid of it.
Right. So I got y squared out of x squared, but that's not really any, well, I don't know. That's not that's not what we wanted. Well, let's see. So now that I've got, so see, so if I have both x squared and y squared, see, that's not helping me yet. So I want to get something that has like x is equal to what? So what is x equal to? So it's like, I don't know. So it's like, I don't know what operation I'm supposed to use. I just like, I could like take something symmetrical with an x squared in it, something with plus some x squared stuff, some symmetrical with some y squared stuff.
This is very interesting suggestions you're giving here. Go ahead, yeah.
Well, it's not work. So I don't know how to get, see, I just don't know how to get this damn x
Yes.
by itself.
Yes.
Things that I've got to have something. I got to deal with linear things in x and y at some point.
Yes.
So I can use x plus y.
Yes. Yes.
Let's see. Oh, I've got x squared and then I've got y squared. What is this now? This. Oh, well, no. Let's see. Oh, wait a minute. So I've got I've got x squared and y squared in my bag so far, right? So
well,
I can.
Oh, you've got y squared in your bag.
Yeah, because I managed that was my brilliant move so far, is I managed to get y squared, and I thought, well, that's no good. But now I'm feeling happier because I could do x squared minus y squared over x plus y, and then I get x minus y. Aha, now I'm happy. Because now I've got x plus y and I've got x minus y in my bag. And so now I'm happy.
Now I'm wondering whether you're doing it a different way from where I was thinking. Go ahead, yeah.
And then I can just add those two and divide by 2. And I get x. Ta-da, I did it.
Can you see this?
So you want it all in one formula?
Yeah, because I want to see if this is exactly the same way as I would do it, or is it?
Okay. So why did I say this? Sorry, this is sorry, I was sort of being stupid. I was writing as I was thinking. So
there's something very suggestive about the way you're doing it. Go ahead, yeah.
So what I do, sort of reading.
You might be hinting at the general way to solve this problem, but go ahead. Go ahead.
I don't know the general. So I'm saying x is x plus y times x minus y.
Yeah.
X minus over 2. And x minus y is x squared minus y squared over x plus y. And x plus y is symmetrical, so I get that's okay.
Yeah.
And then, so then reading backwards. So the way I got x squared minus y squared is that you gave me x squared, and then I got y squared from it by means of this formula here. So I got x squared minus x plus y squared minus x squared minus 2xy. This crud here. This is over x plus y. Sorry, this is like a horrible looking formula.
Yeah, is it?
So this horrible.
How horrible it is going to end up being? Is it, what degree is it going to end up being? Or?
Well, so let me just erase.
I'm struggling to follow along here. I'm sort of.
I shouldn't be. I know it's bad to erase your one steps, but I just Don't
Right.
want to jump over to a new page and lose all my work, lose what I was thinking. So what I'm claiming is that if you do this stupid formula, it works. And so maybe to make it a little bit less obnoxious looking,
Yes.
maybe I multiply the top and bottom by x plus y. So I get like x plus y squared plus x squared. All this is over this fraction. I'm multiplying the top and bottom by x plus y. So the bottom has this 2x plus y in it now. The top has this junk in it. So, what? What?
Yes, I'm guessing that you really are getting the same as my answer, but go ahead, yeah?
Sorry, isn't that right? Really, I'm subtracting that out, so I didn't need that. What? Okay, maybe I was maybe I'm like doing something really roundabout here. Sorry, I feel like I made an algebra mistake because this is sort of weird. So it seems like this x plus y squared that I used here just cancels out. Is that really right? So I multiply that. So if that's true,
There easily could be sign errors in here or something like
there's
that.
got to be some crazy. No, this is ridiculous. Sorry, I'm doing
But I'm
something.
tempted to tell you my answer because it's. Well,
Yeah.
well, go ahead. I mean, if you want me to tell you, if you want me to tell you my answer, I will, and because it's looking very reminiscent of your answer, but I'm having trouble following your.
Well, I'm going fast, and I think I'm making
Right.
stuff.
This is it.
Okay, so all that sneaky stuff wasn't so necessary here. This is clearly equal to x. So this is the real answer.
That's the real answer. That's right. That's right. So you did have some there was some aimless wandering around in your.
Yeah, I was really excited about using x plus y squared.
Right.
That wasn't
right. But the answer that you've just written down is the beautiful answer, the annoyingly beautiful answer. So part of the question is, what's the good way to do this? Is there an algorithm that will just give you this? What? Right? You don't want to do the, if I ask you to define x in terms of x cubed, you'd have to start all over again. But can you figure out something systematic that will show you how to do these kinds of problems? Or maybe I should just tell you. What
is this at all related to this depressed cubic business? Or things like that, this depressed business?
I'm not sure. The depressed cubic is historically important. It's, the Chernhausen transformation or something like that, I think. Don't trust me on this. That's not the way I think of it. Maybe there's something there.
I don't know. It's just wildly guessing. I don't see what it is.
Right.
Oh, you can just tell me what. I don't know exactly what. Anyway.
Yeah. So okay. So let me tell you what I think is the beautiful way to get these kind of answers, and then once we allegedly once we understand this, then that should almost give us enough information to go back and in principle finish inventing the quartic formula, for example. So so the magic words here are Lagrange extrapolation, or Lagrange interpolation, as some people call it, or I guess other people call it Newton interpolation or something like that. So what am I trying to say here? Right. Let me see if I can figure out how this works. So it's like, right, we're trying to invent this function h. We're trying to invent this function h that does what? It takes h, yes, we're trying to get a function that takes h of, well, like I say, this is a function h that has one extra variable. So we'll call the one extra variable, I don't know, t, okay? So we're going to have this function h of x comma y comma t, and I guess it's supposed to be a rational function itself. I don't know, I have to think about that. H of x comma y comma t, and when you plug in, no, maybe I'm saying this wrong. What am I trying to say? H of x comma, yes, when you plug in for t, x squared, it should give you x. Right, this will be very helpful. So this is
plug in for t x squared.
Yeah, but it should be a function of h, t, x, and y.
Oh, sorry.
Or I think it is x, y, and t, but if you want it to be t, x, and y, that's okay.
So
and if you plug in x squared for t, you should get x. Whereas if you plug in y squared for t, you should get y. And that's an abstract Lagrange extrapolation problem. And you're just, so let's actually act. This is, this is easy enough that we can act it out without wasting too much time, which we're now running out of.
Yeah.
So so how do you do this, right? How do you do this? Is just a 2-point Lagrange extrapolation. So it's really just a straight line formula, right? Right? How do you just plot out a straight line formula between?
Sorry, you want h to be linear in t or something? Where's the line? What's linear? What is a straight line?
I think that's right. I think it's going to be linear in t. Yes, that's right. That's right. It's going to be linear in t. So right, we're doing sort of Lagrange extrapolation over the ring of rational functions, or something like that, over the field of rational functions. So the variables x and y are just kind of along for the ride. You can think of them as just honorary constants. So t is the variable with respect to which we're doing Lagrange extrapolation, but it's the most trivial Lagrange extrapolation in the world. It's just 2 points. You have the input and the output at one point, and the input and output at the other point, and you just draw a straight line between them.
I don't get what the rules are. So is this supposed to be like some constant plus some number times t? That's how it depends on t? Is it linear in t? That's how it's got to be? And then it's what in x and y?
Yeah, I mean, c and d are functions of x and y. C and D are rational functions.
Okay. I see. I see.
Right, but I mean, right? I mean, the answer is, to connect 2 points, you just draw a straight line.
Yeah, no, I just didn't get what was
Okay.
linear.
Yeah.
I don't know. You're not going to make me solve this, are you?
Well, I think it's easy to, I mean, we can give up in a moment, but it should really give us the answer that you gave. So what are we trying to say? I mean, right, just suppress the variables x and y for the moment, right? Just think of them as numbers. So we just have a single function. We're trying to say that we're trying to create a function h of t, which has the property that, h of a equals b and h of c equals d. And
yeah,
or right, you can even just draw a picture of, yeah.
so you're like, when something is x squared, you want to get x. When
Yes.
something is y squared,
That's my mental picture, yes.
you want to get y. So you say, I can do it. Yeah.
And you just draw a straight line there. And
That's the hard part.
it's trivial to write down the formula for that. I mean, on good days when I'm awake, it's trivial.
Yeah, I could. Yeah. Right now, I can't even draw a straight line.
All right. I can't see the time here. Let me just, maybe I can look at the time if I look over here. I just want to see the time.
Yeah, I do want to quit on time because I'm
okay.
exhausted and then I have to go do something in an
Sure.
hour.
So yeah, so we really are quitting just about 1 minute. But so yeah, so this is so what we're saying here is if you do this, if you apply, if you just take this most trivial example of Lagrange extrapolation, you will, it will just be this straight line connecting 2 points, and it will reproduce the answer that we struggled to get, which was x squared plus x times y over x plus y. And so that principle, that Lagrange extrapolation principle, if you think about it, that's the principle that we need to apply at the salmon jumps. So that's how we can flesh out the whole quartic formula. I guess there's actually one little tiny piece, one little tiny missing piece that we didn't account for yet. But basically, we have sketched out how you can reinvent the quartic formula for yourself. And, I'm also claiming that arguably this really is perhaps historically how Galois invented group theory, and how all the people who helped him with it helped him to invent it. Because it really is interesting that, right, there was a whole bunch of people who tried to invent, well, there's a whole bunch of people who get some of the credit for the unsolvability of the quintic. But what almost all of them seem to have in common is that for a certain period of time, they thought they could solve the quintic. And they really tried hard to solve it. And they somehow ran into some impassable obstruction. And Galois' version of this was that he basically invented group theory when he's doing this. So
did Galois ever think he could solve the quintic?
I think he was one of those people who thought he could. I know Abel thought he could, right? And I think maybe Ruffini thought he could too. There were a lot of people who thought they could, or they thought they were hot on the trail of inventing.
Yeah, just about. Yeah.
And suddenly at some point they ran into a wall and realized they couldn't do it. So there's a lot more to say, but we're out of time. But this is also a sort of good place to quit because we sort of did finish the 2 main puzzles here. So again, this was not a good exposition of the story, but there is a good way to organize the exposition of the story along the lines of what we're trying to do here. So this was very helpful. But also my excuse for this is that there's stuff that we're doing here today, especially the Lagrange extrapolation, that will be useful to us when we return to some of the topics that we've been studying recently, such as the Artin reciprocity theorem. So that was one of my excuses. That was really my alleged main excuse for doing this. That this role of Lagrange extrapolation in group theory, which we'll have to say more about, turns out to be a tool that we may want to use when we study things like the Galois theory of Z mod 3 torsors over the Gaussian field and stuff like that. But anyway, thanks a lot for listening, and I'll see you next time or whenever.
Okay, yeah, I'll see you. Yeah, I'll have to think about this more.
Sure. As always, there are lots of unsatisfying leftover things, but that's the way it is at the moment. I'll see you.
Okie doke, I'll just quit this.
Okay.
Cool.